Hello friends, in this module we are going to discuss the motion of a charged particle in an electric field. We will consider the motion linear, that is one dimensional, a charged particle moving perpendicular to the electric field and its applications such as cathode ray oscilloscope, corona discharge, photocopying machines and many more. In the study of electrostatics, we have seen that the like charges repel and the unlike charges attract each other. Suppose there are two unlike charges separated by a small distance. If either of the charges is set free, then what will happen? Just guess. The free charge will move towards the other charge, and if the charges are identical, then the free charge will simply fly away due to the electric force. The force of repulsion or attraction between the electric charges is known as electric force. The space or the field in which the electric force is experienced by a charge is known as electric force field. Its measure is electric field intensity or simply the electric field. We define here electric field as the electric force per unit charge. It is a vector quantity. The direction of the field is the direction of the force that would be exerted on a positive test charge. The unit of the electric field is Newton per coulomb. As seen from this diagram, the electric field is radially outward from a positive charge and radially inward towards a negative charge. If a test charge, say q0 coulomb, experiences a force, then the electric field is given by E equals F by q0, and naturally the electric force F equals q0 times E. If the test charge q0 is positive, then the electric force and the electric field are in the same direction, and if the test charge q0 is negative, then the electric force and the electric field are in the opposite directions. Now, let us briefly revise the concept of potential and potential energy. In an electric field, if a charge is moved from one point to another, then the work is done by the system. The negative of the work done is called the change in the potential energy of the system. In other words, the change in the potential energy is defined as negative of the work done by the electric force. Its SI unit is joule. If W is the work done by the force, the change in the electric potential energy delta U is given by delta U equals minus W. We define the electric potential as potential energy per unit charge. The electric potential provides the information about the electric energy without reference to any specific charge. The electric potential difference, or simply the potential difference delta V, is by definition delta U by q0, where q0 is a test charge expressed in coulomb. The SI unit of electric potential is joule per coulomb. It is also termed as volt, and here we have one relation, then 1 volt equals 1 joule per coulomb. Often the quantity electric potential is called voltage. When we deal with atomic or nuclear particles, a commonly used unit of energy is electron volt. 1 electron volt is an energy change experienced by an electron or a proton when it is accelerated through a potential difference of 1 volt. So, 1 electron volt is equal to 1.60 into 10 raised to minus 19 joule. In number of experiments, a precise electric field is required. How do we get it? As seen in this diagram, in a laboratory or in various instruments, an electric field is obtained by applying suitable potential difference across the plates or electrodes by connecting them to a battery or DC power supply. If V is a voltage, that is potential difference across the plates which are separated by a distance, say d, the electric field across the plates is V by d. The electric field can be determined from the rate at which the electric potential changes with position. So, E equals minus delta V by delta S. Here delta S is the displacement from one position to another. The negative sign indicates that the electric field points in the direction of decreasing electric potential. Here we get an alternative unit for the electric field as volt per meter. So that 1 volt per meter is equal to 1 Newton per coulomb. The relation E equal to negative of delta V by delta S is also consistent with the fact that positive charges accelerate in the direction of decreasing electric potential, while the negative charges accelerate in the direction of increasing electric potential.